All right, we're going to talk about chords and arcs now. So we're getting into some new stuff. There's a lot of theorems, but at the end, I'll try and do my best to consolidate all the information for you so it's all in one place so you can try the homework. So, a chord is a segment on a circle where the endpoints are on the circle. So, an example of a chord would be line segment AB. Each chord has its own, you can call it a related arc. And an arc is a part of a circle. So it's a curved segment that's in the shape of a circle. And an example of an arc would be AB with a little arc symbol over it. Okay? A central angle is an angle at the center of the circle with endpoints on the circle's circumference. So this angle right here, let's say it's like 99 degrees. That is a central angle, so angle AOB. Sorry, I don't mean to be in blue. Let's fix that. And the thing about the central angle that you need to know, which is pretty simple, the central angle and the measurement of the arc are always the same. I need you to write that down. Central arc, measure. Oh wait, I messed it up. Central angle measure is equal to its arc measure. So that 99 is the same as this, the measure of this, and the measure of this. So there's a correspondence between that. And that only makes sense, right? If you go around a quarter of a circle 90 degrees, we want this length to be 90 degrees too, because 360 should match 360 for the central angle. So there's like a 1-to-1 correspondence between those numbers. They're equal. Okay? And ones that you probably already know is the radius, which extends from the center to any point on the circle. So like OA. And a diameter is a special chord that goes through the center. So for example, how about AP? So the first theorem we learn actually relates three of these vocabulary terms: the central angle, the arc, and the chord. And what this whole table is getting at, and you can read through it, I'm not going to read it word for word because there's a lot written here, but all you need to know is that these three things, if, for example, if one of them is equal, all of them are equal. Okay? So let's do number one, and I'll show you what I mean. So we have two circles that are congruent, same size, and we have a central angle that's congruent. What else can you conclude? Well, you can conclude that the central angles are equal, of course. But you can also conclude that the chords and the arcs that are related to that central angle are also congruent. So this is the new finding here. So how would you say that? You would say that the chords BC and ZY are congruent, and their arcs, so this arc that the central angle is opening up to, is those arcs are equal too. Okay, so it's like it's all three vocabulary terms. If one of them is equal, all of them are equal. Let's look at this again. So if we know that those chords are equal, so remember it's chords, arcs, and central angles. And they all have to be related, right? They all have to make this shape where you have this triangle here and then the arc. It's these three things. 1, 2, 3. So chords are equal. We're given that, so we know that these are equal to. So how could we state that? Well, let's go ahead and draw in some radii. And we could safely say that if the chords are equal, the central angles are equal, and the arcs are equal too. So again, just remember, if one of them's the same, all of them are the same. That's all it's really saying. And let's go ahead and try and prove one of those. So this one says, if the central angles are congruent, this implies that the chords are congruent. Remember, this word just means implies. It's like an if-then. So if the central angles are congruent, these guys, then the chords are congruent. Okay? So that's what that's saying. So let's go ahead and make a marking where the central angles are. So right now we have A. And we see that we're going for congruent triangles, right? So we're looking for maybe some more sides, at least another side. And the sides on the triangles here are all radii. And every radii of the same circles is equal to itself. So we have 4 different radii, OA, OB, OC, and OD. And they are all congruent. That's a lot of sides, right? Basically every side except for this one, which is the chord length, the one we want. So we could just write that down here, right? We know this is what we want. So what do we have? Well, we have congruent triangles, the blue and the red, because angles, what is it? Side, angle, side? Side, angle, side. Side, angle, side. Definitely. So those triangles are congruent, which means all of their parts are congruent, including this part, which are the chords that we sought to be equal. Okay, a couple more theorems. For this guy, it's called the equidistant chords theorem, which I'm not going to read the text because I think it's a little bit much, but I am going to explain you what's going on in this picture, and what's written here is that if the chords are the same distance from the center, then the chords are equal. And the other way works too. If the chords are equal, then they're the same distance from the center. So this just means chords equal in measure, then the, I'm sorry, these are the chords. The blue chords and the red distances. So this is the distance to the center from the chord, right? So basically, if the reds are equal, the blues are equal, and if the blues are equal, the reds are equal. So if a chord is equidistant, which means same distance from the center, then they're equal. Let's look at, I have plenty of examples here, so let's take a look at those. So for this guy, we see that the distance from O to the chord is, they're equal, they're both 9. So because chords PR and SR are equidistant, they're both 9 away from the center, and because that's equal, that means that the chords are equal too. So if the chords are at the same distance away from the center, they are equal to each other. Okay? So if we want to find out what RS is, we know that this is 12.5 as well because of the markings. And because the chords are equal, we know that SR is going to be 25. Because the other one is 12.5 plus 12.5. chords equal. So for this guy, we see that the chords, this chord and this chord, are congruent because they all have this, they have the same markings. So they're both 15. And because the chords are the same, that means they're the same distance from the center. Remember, it goes both ways. So it's just simply said here that x is 8 because the chords are the same, which means they must be the same distance from the center. Okay? So we have OP and OP prime are congruent. What does that mean? Well, what we just learned is that AB and A prime, B prime are congruent. Those are chords. That's the equidistant chord theorem. They are the same distance away from the center, so they are the same. Okay? And we also have, remember, if you have one, you have them all. So if you have one, if the chords are equal, the arcs are equal. So this chord is congruent to this chord. This arc is congruent to this arc. And remember what the third one was? Central angle. So AOB is congruent to A prime OB prime. Basically the angle that opens up to the chord. Those are equal too. Pretty neat, right? Okay, the last thing I want to talk to you about is the perpendicular chord and diameter. So let's just talk briefly about what's going on in this box. So if you have a diameter and you have a chord, and if they make a right angle, that means that the parts get bisected. So this chord gets cut in half, and the arc gets cut in half as well. Okay? So if you have perpendicular diameter and a chord, they meet at a right angle, make a cross, then the parts are bisected. The chord's bisected. Most importantly is, this one here. Okay? And then the other over here tries to kind of go the other way. It says, if you have a chord that's been bisected, then that means there's a right angle there. So I tried to boil this down because that's what the textbook says, and there's a lot going on. So I tried to break it down, and I lost some of the information along the way, but that's okay. This is the main central idea, is that if you do have a T with the right angle, that means the T gets cut in half. That's the main idea. And then the other way is true as well. If you have a chord that's been cut in half, then by a diameter, then it does so at a right angle. So basically, this is the picture we really want to know. I know this isn't precise, but the little T shape with the two sides of the T, there, if it's a diameter and it meets at a right angle with that chord, it's cut in half equally. So let me walk through some of these. So notice that we do have a little segment through the center. So this could be extended down, and that makes that T shape. Okay? And we're told that it's a right angle. So we know, so this is saying that KN, the diameter I drew in, is perpendicular with the chord. This chord. It's perpendicular. We have the right angle symbol. So that means that this and this, it's been bisected. So we have 7 and 7. Okay? So what does that mean? Well, if we're trying to solve for R, we now have a 3, a 7, and an R. And we can just throw down a quick Pythagorean theorem, where R is the hypotenuse and the radius at the same time. So 9 plus 49, 58. So the answer is just the square root of 58. Which is around 7.6. So this picture is going the other way. We have BC, which could be extended to make a diameter. And we have that these two are equal. They're both equal to 11. So what does that mean? Well, if we go back to our picture, which is a little generalized, but this is what we have. We have this picture right now, right? So that means that there's a right angle. So we have that T shape. We have the T is equal on both sides. So it is truly a T and it has that right angle there. So this is 15 as well, because they are both, these segments right here are both radii. So that's equal to 15. And so I'll write here that, so to fill in what I've written earlier, if the chord is bisected by a diameter, AF is bisected by BC, then the two are perpendicular. Which is why I wrote that right angle symbol. And then if those are equal radii, then their lengths are both equal to 15. And lo and behold, we do have another right triangle. So basically, we said that there must be a right angle there because the T was equal on both sides. The chord got bisected by a diameter. And then we know that all the radii are the same. So that's why we were able to put a 15 on the hypotenuse. So just real quick, we would set up Pythagorean theorem where 15 is the hypotenuse, goes here. And then we would just, go ahead and solve. I'm not really concerned about this part right now, because I think if you really had to do it, you'd be able to. So that's about 10.2. So central idea time. We have this idea that if you have a T and it makes a right angle, then these two parts of the T are the same when this is on that circle. Okay? And the other way around is true. If you have two equal sides of the T, then they meet at a right angle. Another central idea, the equidistant chord theorem, which says that if these chords are the same distance away from the center, then they're equal in length. Okay? And in fact, they are bisected too, because it does make that T shape, right? So, but we know that if this was like 26, then this would be 26, and these would all be 13. So, and if the chords are 26, they're the same distance from the center as well. Okay, so equidistant chords have the same length. And then finally, the other central idea was the first one, which was this merging together of these three new vocab terms, is that if you have a central angle, that one, and the arc and the chord that it opens up to, they are all related, right? If this is equal to this, which it is by vertical angles, then this is equal to this, and this is equal to this. So if you have one matching